In this video, we'll summarize the results of our last lab, which involved potential energies. So we looked at two different situations. We looked at crossbows and gravity, which are going to be related to motion when we address the next section. So it looks like the concept of energy requires two things. You need a force and something has to move. So for the crossbow, when we graph the F versus X graph, force versus distance graph here, it looks like we got a pretty linear, directly proportional graph. And when we graphed the same quantity for gravitational potential energy, force versus x for the gravitational one, we got a pretty constant looking graph here. So the common element was that the area under the curve, which if you think about it kind of encompasses both the force and the distance. If something is in the case of the crossbow, as the string is pulled back, or in the case of gravity, as the object is lifted off the ground. The area accounts for both. There's a force and a distance. As I increase the distance here for gravity, I get more and more area or more energy. As I increase x here for the crossbow, I encompass more and more area or more energy. So equation-wise, or more quantitatively, we know that the area under a curve or the area of a triangle from math class is 1/2 the base times the height. So how does that relate to crossbows? So as you plotted the data and found a best fit line, it looks like this is a number, the spring constant, times x. K was the spring constant, or the strength of the spring. And that's what we found doing a curve fit. So how does that relate to energy? So energy, and I'll say PE, potential energy, due to the, and I'll say the crossbow here, or any elastic object like a rubber band, is 1/2 the base. So the base is, in this case, we'll go to this location, x, and the height is over here, which, if this is x, this is a height of kx, because that's what the equation tells me. This is times kx. So if you multiply this through, you get 1/2 kx squared, which is the equation for elastic potential energy. So I said crossbow here, but it could be rubber band, spring, anything that you can pull and there's an elastic quality to it. 1/2 kx squared. And this unit for energy is a joule. The gravitational case, when we collected the data, it looked pretty linear. And so the area for that is simply a rectangle. So it's base times height. Or energy-wise, it's the x value, that's the base, times the height here, force. And for this specific case, when we pull an object, the force of gravity for an object, if you recall, the force of gravity acting on something is actually mg, the mass times gravity. So we can actually write, and I'll say potential energy due to gravity, is equal to mg, the force, times x. And this unit again is a joule. So when you read the book and you see these equations with 1/2 kx squared and mgx, or in the book it might be mgh, basically the height above the ground, it basically came from the area under the curve. We didn't get to this in this lab, but there's a kinetic energy equation. So if I put a dart in the crossbow and shot the dart or held the dart above the ground and let it go, it would accelerate and gain some kinetic energy. In a later lab we'll see how we got this, but the kinetic energy of an object is 1/2 mv squared, and its unit is also a joule. Kinetic energy is equal to 1/2 mv squared. In all cases, there's a concept called work, which is force times distance. So in both of these cases that we looked at, and I'm going to use a bucket here, I'll call this the potential energy due to a spring, rubber band, crossbow, or a spring, anything elastic. We want to know how it gained energy. So when I pulled, or you pulled the crossbow string back, we actually gave the crossbow some energy. I'm going to use a bucket analogy. And where it came from was by us doing work. I'll say this is you. And you use some of your own energy and you poured energy into this bucket. This is chemical energy that from your food that you eat that's translated into your muscles. So at the end of the day, you did some work by transferring some of the energy into the spring bucket. Or if I take a look at gravity, potential energy due to gravity, when you lifted the block off the ground, the block then had some potential energy. Where did it get the energy from? Same concept. This is you right here. You lifted the object off the ground. You did some work. You applied a force or distance, and you used some of the energy stored in your body to fill up this bucket here. Likewise, if you were to throw something, you could give it kinetic energy. If you kick a soccer ball or throw a baseball or roll a bowling ball, the ball will have some velocity and it gains some kinetic energy. Right here, I'll say K. Where did that come from? Well, you took some of your chemical energy, this is you right here, and you threw the ball, kicked the ball, threw something in the air, and you used some of your chemical energy from the food that you ate again, and gave that energy to the ball in the form of kinetic energy. And this concept of giving energy or transferring energy from one bucket to the other is called work. And the unit of work, again, is a Newton times a meter here, force distance, which we call a joule. So a joule is the common unit for energy. It's a common currency, if you want to call it, for energy. Just like we buy things, we use the dollar. Dollars are a common unit for currency. The joule is the common unit for energy. So in this video you can see how we arise at the concept of energy and where it comes from. For crossbows, gravitational things that are above the ground, or objects that are moving, we do work, we transfer energy into the bucket, and we can quantify it by looking at these graphs. So there's a summary of where the concept of energy comes from.